Hello everyone, welcome to the course on digital signal processing. This is lecture number 2 and in this lecture we will see the IIR filter design using bilinear transformation. So in the last lecture we have discussed about the technique to design the IIR filters. So the first technique was the approximation of derivatives. Second technique we have discussed was the impulse invariance transformation. So in both the techniques there are some drawbacks. So for the last technique, which was impulse invariance transformation, what we observed that the mapping was many to one, means the frequency range which is in analog domain that was mapped in the digital domain, and the mapping was many to one, means many points, many frequencies in the analog domain were mapped in the same frequency range, which is minus pi to pi. So that basically creates a aliasing. So aliasing, that was a drawback for this particular method. So that's why we were not able to design the higher frequency filters like high pass filter, the band pass and band reject filter with the help of this particular technique. So today we have the third technique to design the IIR filters, that is known as the bilinear transformation. So the past two techniques, they are not suitable for high pass or band reject filters. So now in this particular technique, these were the limitation for those existing techniques. So this limitation basically overcomes when the mapping is one to one. So the one to one mapping can be observed in the bilinear transformation technique. So that means the frequency range in the analog domain or in the S domain will be mapped in the Z domain, and correspondingly the mapping from S domain to Z domain will be one to one kind of mapping. So that's why this will not create any aliasing. So this transformation is a conformal mapping that transforms the j omega axis into the unit circle in the Z plane only once. So thus it avoids the aliasing of frequencies. So the transformation using this particular technique means if the filter is stable, if the analog filter is stable, that means the corresponding digital filter in the Z domain will also be stable. If, let's say, the poles of S plane, to see the stability in S plane, we can say that the poles must be lies in the left hand side of S plane, and its counterpart in Z domain, it says that the location of poles will be inside the unit circle. So that is this points declare that the analog filter is stable, and the corresponding the transform filter which is in Z domain, that will also be a stable filter. The bilinear transformation is obtained by using the trapezoidal formula for numerical integration. We are using this particular formula to derive the results. So let us basically consider the system function of the analog filter of this particular type having a simple poles Hs equals to B by S plus A. So the corresponding differential equation can be obtained by expressing the transfer function Hs in terms of Ys and Xs. So this is nothing but S times of Ys plus A times of Ys equal to B times of Xs. Now with the help of inverse Laplace transform, we can basically express this in the form of a differential equation. So the differential equation for our last equation can be represented as dy by dt plus A times of yt equals to B times of xt. This is equation number 1. Now I just want to use the performing the integration both the sides between the limit nt minus t and nt, because we are moving from analog domain to a discrete domain. So on the equation number 1, we just apply the limits, and by applying the trapezoidal rule. So this trapezoidal rule, which is equation number 3, it says that over the limit nt minus t to t of any signal at can be written as t by 2 a times of nt, the upper limit, plus a times of nt minus t, that is a lower limit. So we are going to apply this equation number 3 in equation number 2. So in the left hand side, we can say that this can be written as this integration and differentiation, this will be cancelled out, and we can see that this is y times of nt minus of y times of lower limit, which is nt minus t, plus now in this particular part we are going to apply the a by at by 2 y of nt plus y of nt minus t equals to, similarly to the right also we are going to apply the trapezoidal rule. It says b is a constant, t by 2, and again x of nt plus x of nt minus t. So this is the equation. So this equation number 4, or this equation we can observe while we are using the trapezoidal rule on equation number 2. Now this will further simplify those that last equation, and we are going to apply the z transformation to this entire equation. So it will give us yz by xz of this particular type, which is b divided by 2 by t 1 minus z inverse divided by 1 plus z inverse plus a. This is equation number 4. So basically we have the corresponding system function hz for hs. So if we compare our last equation number 1, let's say, with equation number 4. So equation number 1 was in analog domain or in S domain, that was hs equals to b by s plus a, and this equation is hz equals to b by some factors of z plus a. So by observing both equation number 4 and equation number 1, we can say that the corresponding S plane is mapped as per this factor, which is s equals to 2 by t 1 minus z inverse divided by 1 plus z inverse. So if we will further simplify this, it can also be written as 2 by t z minus 1 divided by z plus 1. So the corresponding, we can say that the z plane can be mapped in S plane, or the or its reverse, which is S plane, can be mapped into the z plane by the help of this mapping factor. Also we must be aware that the generalized expression to map S plane to Z plane is Z equals to e raised to power st. We have already discussed this several times. So on this particular factor, this mapping factor, we can say that when S is basically in analog domain, we must be aware that S equals to sigma plus j ohm. This is S plane, and its corresponding Z plane will be in the form of a circle. So this is radius is r and omega is the angle. So S plane to Z plane we are going to map. So by putting this S equal to sigma plus j omega and Z equals to r e raised to power j omega in this entire equation, equation number 5, we can say that S is in this particular format some real part. Further, if we compare, this will give us this whole quantity is nothing but the sigma, whereas this whole quantity is nothing but the ohm. So in the next slide we can see that the sigma equals to 2 by t r square minus 1 divided by 1 plus r square plus 2r cos of omega. Also the analog frequency and the digital frequency relationship is also mentioned as equation number 8. So if we'll see equation number 7 carefully, it says that when r is less than 0 or less than 1, let's say, less than 1 means it's a region in the z plane, the entire region inside the unit circle. So if we'll map z plane here, so all those points r is less than 1 will be mapped inside the unit circle. So the corresponding part sigma will be negative. So if this is a S plane, so if sigma is negative, so the region is something which is to the left of this S plane. So we can say that if an analog system is stable, means if the poles are lying in the left hand side of S plane, so the analog system side of S plane are going to be mapped inside the unit circle. That signifies that our digital system is also a stable system. So we can say here that on the basis of the real part, we can say that the left hand side of S plane maps the points inside the unit circle in the Z plane, and hence the transformation results in a stable digital filter. That is a very important point. Afterwards, if we'll see that if we'll put R equals to 1 in this equation number 8, so what we can say that the analog frequency ohm equals to 2 by T 2 sine omega divided by 2 plus 2R cos omega. So if we'll further simplify that expression, so we are getting a relationship between analog and the digital frequency as 2 by T sine omega divided by 1 plus cos omega. So if we'll try to solve this further, this can be written as, numerator can be written as 2 times of sine omega by 2 and cos of omega by 2. Similarly, this 1 plus cos omega can be written as 2 cos square omega by 2. So with the help of these trigonometric relationships, we can further simplify this expression as, ohm equals to 2 by T tan of omega by 2. Or interchangeably, we can say that the omega equals to 2 tan inverse ohm T by 2, means this is a relationship between analog and digital frequencies. Here we have the relationship as in the form of tan, here we have in the form of tan inverse. Later on, we'll see that expression number in giving some explanation regarding the warping of frequencies. So that will be going to the limitation of this particular method also. So we're going to see now the relationship between both the frequencies. So at the bottom side, we have the frequency response, or it's a magnitude plot of a analog low pass filter. So in this analog low pass filter, we have magnitude of h of j ohm. So it can be observed that we have ohm 1 and ohm 2, they are the frequencies of, we can say, the pass band and stop band. Also, we have the attenuation as del 1 and del 2. So del 1 is the attenuation in the pass band, whereas del 2 is the attenuation in the stop band. Now, as per the relationship, ohm equals to 2 tan inverse ohm T by 2. So as we can see that the tan inverse graph, it will move from the region will be from somewhere from minus pi by 2 to pi by 2 as per the graph of tan inverse function. Now, since we have multiplied by a factor of 2, so accordingly the graph for tan inverse, it can be something like this. This is pi by 2 and this is minus pi by 2. This is a curve for tan inverse function, maybe tan inverse of theta. So this tan inverse function, basically it's quite important here that in this particular range of theta, this curve increases like this, and to the higher values of theta, we can say there is very less variation in this particular angle. So this basically we have explained, basically we are plotting a curve between omega and the analog frequency ohm. So the frequencies, the digital frequency omega 1 and omega 2 are corresponding to their analog counterpart as ohm 1 and ohm 2. So which I have marked this. Now we just want to transform our analog filter with the help of this particular frequency into a digital filter, filter frequency response. So we can say that here in this particular low ranges of frequency, when ohm is low, so we can see that this variation is large, and accordingly this omega 1 and omega 2, we have this is omega 1 and this is omega 2. But if we are moving further beyond ohm 2, that means we are varying up to infinite in the analog domain, and the corresponding variation we can observe in the digital domain is up to pi only. So we can say that the infinite frequencies in this particular analog domain are mapped in the digital domain between let's say 0 to pi. And if we talk about the higher frequency component, this particular component, so this range is mapped somewhere in a short frequency range in the digital filter. So this is basically the compression of frequency basically. So what happened here is, in this picture we can say that the lower frequency component of the analog domain are going to be expanded in the digital domain, as we can see from this particular figure, whereas the higher frequency component or the higher ranges of the analog frequencies are basically compressed in the higher range of frequencies in the digital filter. So this effect, the compression of the frequencies in the digital domain, are referred to as the warping, frequency warping. So as this equation number 10 gives the relationship between the frequencies in the two domains. So it can be noted that the entire range of omega is mapped only once in the range which is minus pi to pi. So basically this is the advantage. Since in the impulse invariance transformation there was a drawback that the mapping was many to one. So all the frequencies in the analog domain, they are basically mapping multiple times in the frequency range in the digital domain between minus pi to pi. So that creates an intermixing of frequencies, which is called as aliasing effect. So that kind of aliasing effect we are not able to observe in the bilinear transformation. So this is the advantage of bilinear transformation, because aliasing effect is highly not tolerable. However, it can be seen from the past figure that the mapping is non-linear because of the tan inverse function. So the lower frequencies in the analog domain are expanded in the digital domain, whereas the higher frequency ranges are compressed in the digital domain. So this distortion basically introduced in the frequency scale of digital filter to that of the analog filter due to the non-linearity of the tan inverse function. And this effect of the bilinear transformation is usually called as frequency warping in the filter design. So this is also a drawback of this particular technique. So how we can compensate with this type of error or this kind of limitation? So this can be overcome by pre-warping. So let us see what is pre-warping. So the analog filter is designed to compensate for the frequency warping by setting that equation number 9 for every frequency specification, so that the corner frequency or the center frequency is controlled. So this is called as pre-warping. So when a digital filter is designed as an approximation of the analog filter, so the frequency response of the digital filter can be made to match the frequency response of the analog filter by considering the following key points. What are the points? So the first point is the passband frequency, the pre-warping frequency corresponding to Fp. This is in digital domain. Fp and Fs are ohm P and ohm S, and the formulas are quite aware: 2 by T, tan of omega by 2. So for bilinear transformation, again we are going to replace S equal to 2 by T, Z minus 1 divided by Z plus 1. So the designer shall use ohm 1 as ohm P and ohm 2 as ohm S, the stop band frequency, because the factor 2 by T cancelled out at the numerator and the denominator while we are calculating the order of the filter for HZ. So these are the key points which we need to remember while we are going to design a filter. We are going to transform a filter using bilinear transformation technique. So the warping phenomena, basically it eliminates the aliasing distortion which occurs generally in the impulse invariance transformation technique. Also, it is essential to compensate for the frequency warping by pre-warping the given frequency specification of the continuous time system. So, these pre-warping specifications are used in the bilinear transformation to obtain the desired discrete time system or the digital filter. Now, we have a small question over here that Hs equals to 1 by s plus 1 whole square, and we need to solve this. We need to transform this analog filter into the digital system function Hz, and we need to assume t equals to 0.1 second. So the question is quite easy. The mapping factor, we must be aware that the mapping factor is s equals to 2 by t. We can use 1 minus z inverse divide by 1 plus z inverse. Also, I can use 2 by t z minus 1 divided by z plus 1. So, we will use this particular mapping factor from s to z. So, we just replace s equal to this particular factor in equation number, let us say 1, by substituting the proper values of time, which is t equal to 0.1 second. So, we will further simplify this whole expression. We are getting Hz, which is around 0.04 and 1 plus z inverse whole square, and divide by 1 minus 0.90 z inverse raised to power 2. So, this is a system function for the digital filter. So, this question is quite easy. Now this is again we have the transfer function of a low pass filter of the analog low pass filter given by Hs equals to 1 by s plus 1. It's a first order low pass filter, and it is given that the bandwidth of 1 radian per second. We need to use the bilinear transformation to design a digital filter with the bandwidth of 20 hertz. Means the specifications are given for the digital filters, which is 20 hertz, and a sampling frequency. It is the sampling frequency or is also mentioned over here, which is 60 hertz. So generally we observe, we just use a sampling frequency which must be greater than 2 times of the higher frequency component. So we have the analog frequency is given by the bandwidth is 1 radian per second. That means the bandwidth of this particular filter is 1 radian per second, which can be represented as ohm p. The symbols are quite important over here. Also, the desired frequency which we need to design for the digital filter is 20 hertz. So let's say we assume f. We just want to calculate ohm p dash. So ohm p dash is 2 pi fp dash. So we are getting 125.66 radian per second. Now this analog low pass filter can be transformed to a different analog low pass filter by using a transformation. This is called as frequency transformation. Later on we will study that how an analog prototype low pass filter is being transformed to other analog filters like low pass to low pass, low pass to high pass, low pass to band pass, and low pass to band reject. So the formula we are going to use over here is S equals to ohm p divided by ohm p dash. Ohm p dash is the desired frequency multiplied by S. So first of all, we just need to put this value of S in our given expression of the analog filter as equation number 1. So we are getting Hs equals to 125.66 divided by S plus 125. Now the sampling frequency was mentioned, it is around 60 hertz. So definitely it will help us in calculating the value of sampling time t equals to 1 by fs. So t will be around 0.0167 seconds. Now we have both we have the value of t and we have the Hs, we have the transfer function of the analog low pass filter. Now with the help of the mapping factor, we just put S equals to 2 by t 1 minus z inverse divided by 1 plus z inverse. So by simplifying this and by solving this entire equation, we are getting Hz, which is 0.512 1 plus Z inverse divided by 1 plus 0.023 Z inverse. So basically, in this way we can calculate the entire Hz. So similarly, this question can be also this can also be solved. Again, this is the transformation from analog filter to a digital filter. Now there are some limitations, advantage and limitation. Advantage, we have seen that the mapping is 1:1, there is noise aliasing effect, and also if the analog system is stable, so the counterpart digital filter is also stable. There is no restriction on the type of the filter design. Whereas the disadvantage is the mapping is non-linear, so that's why this method, because of this, the frequency warping effect takes place. So frequency warping is the only disadvantage of the bilinear transformation. So these are the references. Thank you.